Welcome to our first webinar here. My name is Landon Garner. I'm the Chief Marketing Officer at Taoglas, and we're pleased to also have Chris Anderson, our Chief Technology Officer, on board as well with us here. Today we're excited to walk through the key antenna considerations that most all of you here on board are looking at, and hopefully give you some ideas and guidelines in terms of what to look for as you deploy and build your IoT solutions. Just to give a little background on Chris before he gets started, he joined the Taoglas team about 5 years ago and has close to 20 years experience in the industry. He's responsible for managing and coordinating our global engineering resources and has been a key part of Taoglas's growth in the last few years. Before coming on board with Taoglas, Chris held positions at companies like Grayhill, Motorola, Spectrum Design, and Digi, among others. Again, he's responsible for all aspects of radio, product development, chip-level cellular, GPS, Wi-Fi, and just about anything else that's really near and dear to Taoglas when it comes to technology. So again, I'll welcome Chris and let him take it away from here.
Hey folks. The key bit of that bio that might be of interest is I used to be you. I used to be a Taoglas customer. I used to do exactly the kind of integrations that you're presented with now, and that's where these seminars came from. Is we wanted to cover the various things that everybody struggles with, that I struggled with when I first started dealing with cellular many moons ago. And so yeah, that's the idea. This is the first in a series of webinars that we'll do. We'll do some additional webinars focused on specifically on points of interest like U.S. cellular certification, performance problem mitigation, what to do when the thing doesn't work properly. And optimization of performance, in particular for GPS and other specialized systems like that. Yeah, so moving on to a little about Taoglas, with the next slide here. Taoglas has been providing RF products of various sorts since 2004. Taoglas started out as a GPS antenna company, focused specifically on ceramic GPS patch antennas, and everything kind of grew out of that. We were just crossing the 300 employees mark. We have 7 facilities globally in countries like Ireland, Germany, Taiwan, the U.S., and now China. Our general biggest area of business is IoT. IoT is our bread and butter. We have initiatives into other things like automotive and other markets like that to grow our business, but our daily bread is IoT. So moving on, diving into the wonders of the details. So this next slide, I want to talk a little bit about link budget. So a link budget, for those who aren't intimately aware, is how you figure out whether your radio system is going to work or not. Radio performance is not measured in units of feet or any other units of linear measurement. It's measured in link budget and in dB, decibels. What it comes down to is, will my radio link work? Well, how much conducted power do you have? How much of that conducted power gets to your antenna? In the little link budget example there, you see some example losses. How much of your transmit power gets to your antenna? And then what's the gain of the antenna? And the reason we're talking about link budget is because I'm going to explain gain next. and how that impacts you selecting an antenna, and how do you judge whether that antenna is a good thing or good enough, and in particular good enough for your particular application. Um, so yeah, transmitted power into your antenna, the antenna gain itself. Then what what real what real world range or distance you get comes from that path loss number. Now, what's really unfortunate is that path loss number is not a simple formula that comes out to meters or feet, gives you X amount of dB, um, because all of the things in the way matter. That sheet of drywall, um, that wooden desk, um, uh, everything that's in between matters. And then it's further complicated by the fact you almost always have more than one path for the RF energy to go. There's the direct path from your transmitter antenna directly to your receiver antenna, but there are almost always reflections, where some of the energy is going from your transmit antenna off the refrigerator in the break room to your receive antenna. And sometimes that helps you, and sometimes it hurts you. Um, and when it helps and when it hurts is completely situation dependent. Um, what this means is there is no nice way to go do uh, range measurements and say this radio uh, this radio has 20 feet of range. This radio has 200 yards of range, um, because if you go and do a test like that, all you can say is it it worked at this distance in this particular situation on this day, and all of those other environmental factors play a part in whether it worked or whether it didn't. Did it rain? Did it not? Is there snow on the ground? Is it not? What is the ambient temperature? Is there fog, etc.? All those things, all that stuff, all matters to path loss. And to a large extent, we don't really have a whole lot of control over path loss. Path loss isn't something that we as product designers get to have much of a say in. Um, we can sometimes mess with transmit power, although with many common radio systems such as Wi-Fi and cellular, you don't. It is what it is, and you can't turn it up anymore. Um, you can change the gain of the antennas, the transmit and the receive side, and that's through antenna selection. And then receive sensitivity is again usually set by the radio involved. So on the receive side here, that link budget goes down. You have the various losses. You have the receive sensitivity. That's the conducted receive sensitivity. That's in the data sheet for your radio chip or your radio module. And then the EIS number you see there is when you add up all of those losses. That's the effective sensitivity. Um, when you add up the when you add the effective sensitivity number there to the received power number on that link budget, it gives you your link margin. And the key takeaway is, if your link margin is negative, your radio doesn't work. Your receiver can't hear the transmitter. If your link margin is 0, then you're right at the bleeding edge of it working or not working, and basically any variation in the environment, people walking by, um, a semi drives by and blocks your path. Any kind of variation in your environment will break your link for at least a short period of time. In general, you want to target having an absolute bare minimum of 10 dB as a link margin, and that's a risky link. 20 dB is a more standard number, um, and anything better than that is more gooder, as they say. The last piece of information on this link budget slide, the last takeaway, is to get a feel for the numbers. With a typical conducted receive sensitivity Minus 92, that's would be typical for a cellular type radio. Transmitted power of 20 dBm, not that far off from a typical cellular radio, depending on which kind and all that sort of stuff. Um, and so your total link budget, what you have to work with, is often well over 100 to 120 or so dB. Um, and that sounds like a lot, and it is, which is why it works. Which is why radio is so useful in terms of throwing photons from one place to another and being able to do something with them when they get there. But um, this kind of gives you a scale for understanding the next bit about gain. How much? What is this gain stuff, and how much is good enough, and where does that take us? So if we go to the next slide. So antenna metrics. So there's this gain thing. So there's basically two variations of gain that we antenna designers are always talking about. We're talking about average gain, which is the gain in all directions um, of the antenna, and average gain is a measurement of basically of the amount of energy I put into the antenna, how much actually gets radiated in any direction. Um, and then the other number is peak gain. And peak gain is when I put energy into an antenna, um, which there's going to be some specific direction where there's a maximum in the amount of energy uh, radiated. So um, average gain doesn't have any direction aspect to it, any directional component. Um, Peak gain does. Peak gain is the gain in a specific physical direction. Which one of those you get to use depends on the reality of your product and your system, your radio system, and what the details are. One quick side note: antenna people, we always love to just keep everything in dB. You saw that link budget earlier; it was all in dB. We like talking about antenna gain in dB because you can directly put it right into that link budget. And once you've got a feel for how that works, it can be kind of intuitive. For instance, if you have for average gain, 0 dB average gain, and it would be 0 dBi or 0 dBd because you're comparing the gain of your antenna to some reference. dBi means you're comparing it to an isotropic radiator, a perfect antenna radiator. dBd means you're comparing it to a dipole. Um, the difference is 2.51 dB. So a dipole would be 2.51 dBi in those terms. So let's see here. So where I was going with that is we like to keep those things in dB. However, and so 0 dBi is a perfect isotropic radiator. It's a perfect antenna. Obviously, it's extremely difficult to build a perfect antenna, and realistically, a -3 dBi gain, average gain antenna is considered a really good. That's a really good thing, a really good physically manufacturable antenna that you can actually build and sell. -6, a -6 dBi average gain antenna is still that's still an okay antenna in the context of that link budget that you just saw there. -6 is okay, but it's not great, but it's not terrible. -9, -9 is pretty bad. -9 is not a very good antenna. When you consider the fact that in most radio systems, the antenna typically will use the same antenna on both ends of the radio system. There are exceptions such as Wi-Fi and cellular, but a lot of other earlier radio systems like land mobile and stuff, you'd be using the same antenna on both sides. So if both antennas are -9, that's 18 dB out of your link budget because it kind of it hits you on both the transmit side and the receive side. And then oh boy, minus 12. Minus 12 is awful. Now the reason I went in jumps of 3 there is because every time you have 3 dB, that's half the performance of the antenna. Um, so a 0 dB gain and dBi gain antenna, if you put that in linear units, which again, antenna people don't like to use linear units because it it's not a linear behavior. However, it is more intuitive for people who are not coming from a radio design background. So that's where we come up with percent efficiency. So you'll see on all of our data sheets, we'll have both average gain in dB and percent efficiency listed. Those are exactly the same measurements, but they're being displayed in different units. Um, so 100% efficiency is 0 dBi gain, 50% is minus 3, 25% is minus 6, um, and 12.5% is minus 9. And yeah, nobody cares about minus 12 because that's crap. That's just not a useful antenna. You might as well just have a paperclip. So so that's a little bit of background on the average gain side of things. So then there's this thing, radiation pattern. So radiation pattern is a graph. Um, well, actually, we graph the radiation pattern. The radiation pattern is literally what direction does the energy go when you put the energy into the antenna. There's 2 radiation pattern plots on the screen there. Those are examples of GPS antennas. The antenna on the left is called a quad helix. This is a very, very high performance GNSS antenna that Taoglas sells primarily into high precision, like precision agriculture and things like that applications. The advantage of the quad helix is it has extremely good, extremely even radiation pattern. It looks in basically a whole hemisphere equally in performance. This is particularly useful for GPS or any other low Earth orbit satellite constellation system like, say, Iridium, because most of the satellites are not straight up. Most of the satellites are off at an angle. Uh, the more sky there is, the further you go down in angle from zenith, the more sky there is to have satellites in, and the greater the likelihood that there are satellites there. So, from a strictly speaking, from a performance standpoint, the quad helix is the way to go when it comes to GNSS. The patch antenna radiation pattern on the right side illustrates an antenna that has a directional characteristic to it. The quad helix on the left is as close to an isotropic radiator, that is an antenna that radiates equally in all directions as you can physically really get. The patch antenna on the right side is a good example of a directional antenna. In this particular case, it points up. And yeah, the nice thing about patch antennas for GNSS, of course, is they're physically small, they're relatively cheap, um, and they are still circularly polarized. Both of these antennas are have circular polarization. I'll talk about circular polarization in a minute. But what it illustrates is the patch antenna focuses its attention, if you will. If you were transmitting with it, it would be focusing its radiated energy. If you're receiving with it, it does its best job of harvesting that incident energy, if that incident energy is coming from straight up. So, as in all things engineering, these things are trade-offs of performance versus cost and physical size, and that's why you see most people actually use patch antennas. So the idea with peak gain is, in the case of the patch antenna there, the peak gain is straight up. Well, the peak gain for that antenna isn't negative. You can't have an average gain that's positive. It's always negative because it's not the definition of average gain is such that 100% efficiency is 0 dBi gain. Well, when you focus the energy in a particular direction, now you can have positive gain. And if your application supports that situation, Now that could be very, very powerful. Um, and so there are situations where you can do that and situations where you can't. In the case of GNSS, um, yeah, we don't really care a whole lot about that added gain at zenith because there probably isn't a satellite there statistically anyway. And even if there were, that's actually the shortest distance, the shortest propagation distance from my antenna to the satellite. So that's kind of the easiest case. Um, Again, we use patch antennas. Everybody uses patch antennas because they're cheap and small. Uh, but the idea there to finish off with peak gain is if you have a situation where uh, you know the orientation and or location of of the transmitter and receiver in your radio link, you can optimize the radiation pattern to get significantly better performance, uh, as long as you can guarantee those locations and orientations. One example, the stereotypical example of that is to use an omnidirectional antenna, which basically has a radiation pattern that looks like a donut. Omnidirectional antenna focuses its energy in a plane, typically an XY plane parallel to the Earth's surface. Um, because if you know that your thing is somewhere on the Earth's surface, then there's no point in having good radiation coverage straight up or straight down. Um, you want it to be out to the sides. That's a good example where using an omni antenna, now instead of say a -3 dBi gain antenna, you get to use the peak number, and a 2-element collinear could be +5 dBi, um, and so that can be a pretty significant difference. Um, which thing you get to use, whether it's average gain or peak gain, is completely dependent on your application. For cellular, and pretty much almost always for Wi-Fi too, it's generally assumed that you're going to use the average gain number because you can't count for what the orientation of the handset or the Wi-Fi device is. Um, on the base station, on the cellular base station, of course they spend a lot of time creating really good radiation patterns that are sculpted on a per cell site basis to create optimal coverage. Um, they can specify what they want to do on the base station side, but on the handset side, it's the average gain number that you end up having to use. Um, uh, yeah, so that's the bit about that one. Let's move on to the next slide here. Environmental factors, the nature of antennas, if you will. So all antennas are affected by their environment. They're affected by that piece of plastic right next to it. They're affected by that battery nearby, that LCD screen. They're affected by everything um, within a reasonable coupling distance. How big is a reasonable coupling distance? About that 20 millimeters that we normally talk about in our data sheets. You'll see that in a lot of our data sheets, um, we'll specifically say, this antenna should be used, for to get performance consistent with what we talk about in our data sheet. The antenna needs to be used at least 20 centimeters away from other things that could affect the antenna, such as any metallic object, or even plastic materials. Now that's not that realistic for internal antennas. When everybody's trying to build a product, of course, that product needs to be small, it needs to be physically small, and and when you're doing that, you tend to end up shoving all of the system components all close to each other, and the antenna doesn't really get out of that mess. The antenna gets to participate well. And the key thing to take away from this slide is um, all antennas are affected by the stuff around them. Um, there's a couple ways to handle that. If you use an antenna that has a very, very wide efficiency bandwidth, And a good example is the Taoglas FXUB66. Um, uh, that antenna has such wide bandwidth. You can put it next to pretty much anything, and while putting it next to a big metal surface, or putting it directly on a thick polycarbonate slab will disturb its performance. Um, that the antenna has so much bandwidth that even though you've disturbed its performance, it's still a really good antenna, uh, because its tuning may have shifted, but it's it's it can't shift enough for it to get out of band, as it were. Um, yeah, bandwidth. Bandwidth comes from size. Um, a lot of people will say, "Hey, I want a really good, really great performing cellular antenna, or dual band Wi-Fi antenna," and I'll recommend the FXUB66, and they'll say, "Oh, but it's so big. It's about the size of a dollar bill, a U.S. dollar bill." And I'll say, "Yeah, but it works fantastic. Um, we have other products that are physically smaller and they're much harder to use, um, which is why we'll help you. Um, uh, but when you need something to just peel and stick, fire and forget, slap it in there and move on to your real problems, that are, the core competency of what you're trying to address. FXUB 66 is a really solid choice there. Um, Now, as I was saying, with internal antennas, oftentimes you can't do that. So you run into two situations. Um, the best way to handle um, environmental effects detuning an antenna, is physically. So there's certain things you do to the environment of the antenna, such as you can't put the antenna sandwich the antenna between the battery and the printed circuit board. Those two things are conductors. They block the radiation pattern, and there is nothing we can do to fix that, because you're trying to throw those photons as hard as possible, and if you throw them at a metal sheet, um, they don't go anywhere, and then therefore that is wasted energy. Um, and that takes, for those in the cellular side of things, that shows up as poor antenna efficiency and/or poor TRP. Um, so part of it is physically make sure your antenna has a useful view of the world. Your antenna needs to be able to see out and radiate out of your product, without stuff being in the way, in particular metal stuff. And then the other part of that is, um, plastics and other dielectric materials. And for you guys, it's probably going to be mostly plastics, although glass shows up a little bit sometimes. Um, those things can detune an antenna as well. And what we will usually do, in that situation, is we will physically tune the antenna. Tuning the antenna is the process of making physical changes to the antenna itself. Um, and a real good example is, GPS patch antennas are very sensitive to their environment. Um, uh, they they practically always have to be tuned, in order to have the best performance. They practically always have to be tuned to the environment around them, the plastics, the screens, any of that kind of stuff. Um, and that's a service that we do, and we do it quite a lot. We'll take the standard part, in a customer's sample. It could be a quick turn sample PCB that was, a little $300 thing, from, a 2-day turnaround service, with a 3D printed enclosure and copies of your LCD screen and your battery that are just shoved in there and not electrically hooked up to anything. Um, but we can take that stuff, we can take that physical mock-up, go and tune that GPS patch antenna to that environment, and now it'll have the best possible performance. And then that gets issued a new part number, and then you buy that part number from Taoglas, and that antenna is specifically designed to work in that application. Um, so, excuse me. So, antenna tuning, antenna optimization, um, is how you actually get the best possible performance. Um, there are certain aspects in particular of circularly polarized antennas, such as patch antennas used for GNSS, um, that can only be physically tuned. The axial ratio, the quality of the circular polarization, um, is something that can only be physically adjusted. It's not something that can be done with matching components. Which brings me to the other way that you'll see these things addressed. If you, for some reason, you physically can't make modifications to the antenna, can't or don't want to, you can do this. You can do a impedance match, where you're typically taking some combination of inductors and capacitors and adjusting the impedance match of the antenna, and thus adjusting its optimal frequency, its optimal efficiency frequency, um, and and compensating for it being dragged off frequency by dielectric loading. Um, you can do that, and if you're doing that at one frequency, it's pretty painless. If you're trying to do that for a really wideband antenna, multi-band antenna like FXV66 or any other cellular antenna, that can be pretty challenging. It Those are things we do all the time, but it's definitely not something that you'd want to start out with yourself as your first matching exercise. And then the final takeaway on that is matching components can be used to get the best efficiency efficiency tuning for an antenna, but they don't affect polarization. So you can't use matching to fix axial ratio for a circularly polarized antenna. You can only do that with physical tuning. Um, so yeah, again, the takeaway there, excuse me, comes down to um, uh, everything around the antenna matters, um, and the closer it is, the more it matters. Let's go on to the next one. What we typically see is for antennas that are bigger, antennas that are used for frequencies higher than 1.5 gigahertz. Um, you don't really typically have to make much of a size trade-off. The antenna is typically already small enough that um, that it can fit into even relatively small portable devices and still have good performance. Um, and so above a gigahertz and a half, it pretty much can be as good as it can be anyway. Below a gigahertz and a half, you start, the lower in frequency you go, the greater this factor is. You end up often having to trade performance for size, and the smaller your antenna needs to be, the worse your performance is going to end up being. And this is a factor of physics that isn't anything anyone will ever be able to affect. There's no magic that will ever make this change. Um, some good real world examples of this would be your typical garage door opener. Most garage door openers at 300 or 400 megahertz, and they physically usually have just either a printed trace in there on the printed circuit board, or a little helical coil. Um, those antennas are extremely small relative to the wavelength involved for those frequencies, and yeah, that's why your garage door opener doesn't work more than about maybe half a block. Um, if you had 0 dBi average gain antennas on both ends of that link, with the same transmit power and receive sensitivity, you would get many blocks of effective useful range out of it. And this is just another example of that is remote keyless entry. Similar frequencies, even smaller transmit powers, and even smaller antennas, and that's where you see all that come out. For that reason, that's why the cellular guys really like spectrum between about 600-700 megahertz and about 2 gigahertz, 2 or 2.5 gigahertz. That's the sweet spot where you can have the antennas fit inside the handset, be really efficient, um, and still have halfway decent building penetration and free space propagation. So, um, so the other bit on this slide is, yeah, you as the system designer can generally make that size versus performance trade-off, unless you're doing a cellular device in the U.S. because the cellular carriers have already decided that they expect a specific certain minimum level of antenna performance, um, and because of that, that in turn dictates a specific physical minimum size. Um, and this is a key thing for anybody who's interested in doing wearables, especially wearables for cellular. If you're doing a wearable device that's going to use Bluetooth to talk to a phone, you're golden. If you're doing a wearable device that is supposed to have LTE in it directly, um, there are lots of conversations that have to get had because it's not possible to make a wristwatch um, that has cellular in it that meets the U.S. carrier requirements. So to be clear, that Apple Watch, that Samsung Watch, that LG Watch, they do not meet U.S. cellular carrier requirements. They only exist by virtue of waiver. Um, and getting waivers is part of the cellular certification webinar that we'll end up doing here at some point soon, because all of that is a whole new ball of wax. Uh, so let's see, moving on to so self-quieting is an industry term. It's an old Motorola term that relates back to what happens when you have a carrier signal, a jamming signal on an FM voice radio? And the answer is it's quiet. Instead of playing static when you turn the squelch all the way down, it doesn't do anything. It makes no sound. It's quiet. So that's where that comes from. Excuse me. And so the item here for the for what we run into all the time is most of our customers are building some kind of product that does something, and that product that does something for some reason needs to have a radio. And so from most Taoglas customer points of view, that thing isn't a radio. That thing is it's a tracking device. It's a data router. It's a computational device. It's a sensor. It's whatever that thing is supposed to be, right? And it just has a radio in it. Well, the unfortunate reality is once you put a radio in something, that product is a radio, both from the standpoint of say FCC or ETSI certifications, and for this whole aspect of actual performance measurement. So the number one problem that folks have when building, especially their first radio device, but all radio devices, is this issue of self-interference. You've got a microcontroller. That microcontroller has Ethernet and USB. Those Ethernet and USB peripherals have PLLs, those phase lock loops that are generating uh, the, the core frequency that's running that peripheral. Typically, you'll also have some sort of high-speed memory bus, and that high-speed memory bus has a huge array of different clock frequencies going on because the address and data lines are not moving every single clock cycle, so they're moving at some subharmonic. These are very typical examples of system elements that generate RF energy, and generate RF energy that is in band, that is at the same frequency as your radio receiver. When your antenna is very close to to the sources of that radiated energy, that radiated RF energy, um, those sources can be very quiet. Those sources can be perfectly compliant with FCC or ETSI spurious emissions requirements. Um, well, those spurious emissions requirements are there to make sure that your thing doesn't interfere with somebody else's thing that's a meter away or so. Well, your antenna is not a meter away. Your antenna is centimeters away, if that. And that's where things really get painful because um, when you when you when you start dealing with this self-interference issue, um, you generally can't shield the radio um, from the antenna. They're right next to each other, and so you're presented with the situation of all you can do is fix the electronics, and fixing the electronics is a very arduous thing. Um, it's something that we have a lot of experience with. I and the team here in Minneapolis, in particular, um, made our living fixing radios, fixing these exact kinds of problems for quite a while before we decided to go work for Taoglas and do antennas. And so that's something that we offer as a service. There's a service we offer called ISA 20, um, where we'll go and look at a customer's product and come back with specific feedback on put this specific value of capacitor here and put this resistor here and put this filter here and change this PCB layout trace and there's about 170 or so RF best practices um, that were on our checklist the last time I looked, um, and and we've been doing this for the three guys I have here in Minneapolis that focus on this. All have a decade of experience doing this stuff, and we still learn new things and come up with new ways to mitigate these issues as we go. Um, the key to self-quieting and self-interference is test early, test often, find it early, be afraid, and and just know that everybody has this problem. This isn't using using an off-the-shelf radio module doesn't fix this. Doesn't make you immune to this. Um, and, and radio designers who have decades of experience, their first prototype often has self-quieting. It's just a normal part of radio development. Um, what's not normal is finding out about it when you think the whole product is done. When you go, in particular with cellular, you go and do TIS testing, and oh, we're 20 dB off from our radiated receive sensitivity number, and the carrier is not okay with that and isn't going to let us sell our product. Well, yeah, uh, definitely not something you want to find out at the end. So let's go on to the next one: antenna type versus risk. So um, the key takeaways here are that whole thing I was just talking about with self-quieting. If your antenna is physically not next to your electronics, then you can't have self-quieting. So if you use an external antenna, basically you're practically guaranteed to not have to worry about that. External antennas have the lowest project risk, the lowest certification risk, and the lowest performance risk. The antenna is already tested, it's already designed. The data sheet clearly states exactly how well it works. It's ready to go. The external antenna is the way to go to get to market quickly. When customers come to us and ask, what's the best solution for an antenna, I will always tell them, first, start with an external. Even if your product, even if you acknowledge that your product eventually needs to have internal antennas, that's fine. Make your first prototype with external antennas, so that you can take that and you can go out and experiment and you can do real testing with it, and you can give it to customers and say, yeah, I know it's not as pretty as you'd like it to be, but it does it do all of the other things? Does it meet your other use cases and your other mission demands? And so, um, what by looking at those things, this often can bring a product to market With external antennas, the first version with externals, much faster, which with much less business risk. Um, Externals, lowest risk, some of the best performance. Yeah, they cost more than internals, and they're an external thing. They're physically larger than internal antennas. Um, when you're dealing with vehicles and telematics and stuff, however, they can still actually be the total best solution in the end, just because you're able to mount the antenna in the best place in the vehicle and situations like that. Terminal antennas. Terminal antennas are a halfway step between externals and internals. Um, you still have low risk on the performance side. The antenna has been tested it screws onto a ground plane the way you're going to use it, so you know how well it's going to work because it was tested that way in the data sheet. But you are putting the antenna close to your electronics. Because you're next to your electronics, you now have a much greater likelihood of having that same issue with self-quieting. That said, because you're screwing onto a bulkhead connector, it's possible to fix any self-quieting issues if you're using terminal antennas with brute force shielding. That is, slather the inside of that enclosure, that plastic enclosure, with copper tape, or just make sure that your metal enclosure has really good electrical connections between all of its pieces, and you can keep that noise inside the box, and off you go. Uh, and so it leaves you some other rooms for mitigation. Internal antennas, all you can do is fix the electronics, and that a lot of that is also the pure performance details are controlled by the physics of your enclosure. So it's much more interactive and sensitive to the mechanicals of your system. Um, the key takeaway on that one is if you're using internal antennas, you really want to design your product around the antenna from the get-go. Um, the first conversation for your mechanical engineer, it should be, what antennas do we need and where do they have to go in order to make this product actually function and work. So we'll go to the next one. Um, yeah, there's a number of unfortunate things going on in the industry and just physics. One of them is uh, so T-Mobile went and bought some 600 megahertz spectrum. So all of our antennas that got bigger in order to go from 3G to 4G to support LTE on the 700 megahertz band for Verizon and AT&T. Now we need to make them even bigger in order to support the 600 megahertz band for T-Mo. That's physics. There ain't no way to get around that. It is what it is. We currently have, I think, 3 products in development that we'll be releasing that explicitly support T-Mo's new 600 megahertz spectrum. But yeah, size is proportional to frequency. Um, Another big part of that is physics doesn't care about customer expectations. Um, if just because the rest of the electronics can be made smaller, such as a wristwatch, a personal emergency response pendant, products like that, dog collars, those sorts of products can be made smaller, but the antennas that they need to use can't. And so that's something that needs to be factored in as part of the product design. As I said earlier, um, you need to design your mechanicals around your antenna, or you will end up having to design an antenna into your mechanicals. Um, Using an off-the-shelf antenna on day one and using it the way it was designed, everything is just going to be so much simpler. You're practically guaranteed to get the performance that you need for proper system performance. It's very possible if you do it the other way, where you design the enclosure first, it's very possible to design an enclosure for which there is no antenna that can be made to make that work. You can paint yourself into a corner where you have to start over. Um, We have a number of services related to these things. ISA 10 is a service that we offer around what level of performance is sufficient for your product. What antennas can we propose that meet those performance requirements, and how would you implement those antennas to meet those performance requirements? Um, that's a pretty straightforward, quick process for us to do. Um, it's normally something that our customer, that a system designer for their product would do. But a lot of our customers don't have that background, and so that's where a lot of these service offerings come in. Is um, is applying our experience of doing radio product development uh, in a way that helps our customers get good time to market, time to volume. Um, another related one there is CSA 20. CSA 20 is a service we offer. You can build a physical mock-up of your product. Again, 3D printed enclosure, quick turn PCB, stuff like that. Send that to us, and we'll measure it. We'll measure it in our anechoic chambers. These are fully CTIA compliant anechoic chambers, where we can go measure that performance, and we can tell you exactly how well that's going to perform. And consequently, while your electrical engineer is doing schematic capture for the rest of your product, if your mechanical engineer knocks out a mock-up like that to send to us, we'll be able to tell you whether that antenna is going to be good enough before you even get that first prototype electrically built up. And now this is huge amount of project risk that's removed right away at the beginning of the project. And if for some reason it's not good enough, you can pivot and fix it right away before you've gone too far down any particular path, either physically with tooling or something like that, or from a marketing standpoint in terms of setting size or shape or design expectations. So yeah, that's pretty much the last bits there. Um, I guess we can move on to questions.
Yeah, great. Thanks, Chris. Yeah, super insightful. A couple questions came out. I'll play moderator here a little bit. One question we got was, I think you may have answered it just a couple seconds ago, but in terms of PCB layout, is that a service that Taoglas would offer to customers?
That's a good point to clarify. Taoglas is not a design services company. We are not in the design services business. You'll be happy to all hear, I'm sure, that all of those services on our website, all of those services except one, are fixed bid. They're fixed fee. That they're not time and materials. Um, the flip side to that is we do not do schematic capture or PCB layout. As part of the ISA 20 review service, we will review your schematic capture and PCB layout and mechanical details in trace by trace, component by component, BOM line by BOM line, gory detail. Um, but the creation and management of those design files and the product in general is always our customer's responsibility.
Yeah, and to add there, we have a great network of partners that we can refer you to on that front. Another question here, Chris, that came along, just to talk maybe through dev kits, specifically maybe some of the newer low power wide area technologies. Are we suited to be able to support development kits on that side of things?
Absolutely. We've historically done a fair amount of engagement with providers of radio modules of various sorts, cellular, GPS, Wi-Fi, Bluetooth, things like that. And we're definitely interested in doing that same thing with the various low power wide access technologies. Um, a lot of what we get asked about for, say, LoRa and Sigfox and things like that tends to be the base station side of things. So it tends to be external, big omnidirectional antennas and stuff like that. We do already have a very wide selection of antenna products for 868, 915, and obviously 2.4 gigahertz. Um, we're always interested in understanding more about specific market drivers, and so if there are particular applications that our current products don't address, I'd love to hear about it so I can make new products that do. Um, and when it comes to working with dev boards, that's and getting designed into to development boards and evaluation boards. Um, yeah, that's a good business channel and sales channel for us, and we're very much interested in doing that.
Great. Yeah, just we just have time for maybe one or two more questions here, although we have a couple more. We will address all the questions in a follow-up email. So if you didn't get your question answered, we will address that. Also, to answer one of the questions that's been asked, there will also be a recording of this webinar, so you can take it back to your teams or internalize it a little bit further. So we will make that available via email also. Um, Real quick here, Chris. One question is, how effective is embedded or buried capacitance in PCB board stack up compared to RF shielding of microprocessor sections to minimize self-quieting? Kind of complicated there, but
Mm, well, I mean, they're kind of a little bit separate. So distributed capacitance, is obviously going to get you bypass capacitance, and that's always useful. Um, Typically, however, we see it's better to use specific capacitors on traces that are either susceptible to incoming RF emissions or might radiate RF emissions from them. In particular, for instance, the power supply lines on the PLL for Ethernet, main memory bus, and USB. Those would be really good examples there. Um, for shielding, so for transmission lines and things like that, um, excuse me, for shielding aspects, if you're going to run, say that memory bus, you got to have an external main memory bus. Running all of those traces for that memory bus on inner layers and having ground pores on the outside is a standard RF best practice technique. It's one of the first things that we always look for. Um, if you absolutely can't, and you have to be running high-speed digital traces on a surface, then yeah, there's a high likelihood you're going to end up having to have a metal can shield. Um, but running high-speed digital traces on inner layers where you've got copper ground pores on the outer layers to create shielding is a really, really good way to get that shielding basically for free, um, and keep everything cheap and small and efficient.
great. And last one here, we just have 30 seconds left here, but quite a relevant question. Customer that has a 2G or 3G device with a Taoglas antenna today, obviously with a lot of the carrier movements, especially in the United States, that push is coming rather quick here, specifically to, well, 2G is kind of already taken place, but 3G sunsetting not too far off. How easy is it, or can you reuse essentially the same antenna if you drop in a new maybe Cat M1 module or LTE module?
In North America, basically you can't. Unfortunately, coming from 2G or 3G, um, uh, would have been dealing with a lowest frequency of the 850 megahertz U.S. cellular band. Um, Now, Verizon, AT&T, Verizon and AT&T and T-Mobile all have 700 megahertz spectrum that they're expecting that they have LTE deployed on, and whether you're doing Cat 3, Cat 4 for speed, or whether you're doing Cat 1 or Cat M for cost and power, all of these guys have to support those low frequencies, which means your antenna has to change, and your antenna has to get bigger. And yes, that is exactly as painful as it sounds. We deal with that all the time, and that's something that our field application engineers and our antenna development engineers can specifically help with to try and minimize the amount of pain. It is possible sometimes to make changes to the system so you can reuse plastics and enclosure type pieces, but you're guaranteed to have to make significant changes to the electronics.
Okay, great. Well, thanks. Unfortunately, that's all the time that we do have today. But as I said, we will get back to any questions that were left unanswered and look for a follow-up email with those details as well as the recording to this webinar. And we will also keep you in the loop with future subjects that we'll cover via the same medium. Appreciate all the time that everyone's taken, and especially wanted to thank Chris for his expertise. And we will talk to you later.